that motion, we talked about the position, we talked about this, yeah, we talked about the velocity, we talked about the acceleration, linear momentum, force, and all these things we calculated, right? And if the external force was zero, then the momentum was all these things. Now we will understand about the purely rotational object, right? But before we do that, we will need this cross product or the vector product. So I will recap these and yeah, I will ask a question and then we will move on, right? So what we have done so far, we have done a translation motion, and in that we have talked about this displacement, which is, let's say, x, right, vector, and then we had this velocity, which was v, and then we had this momentum. So all these are linear displacement, linear velocity, linear momentum. This was p, and then we had this linear acceleration, and then we had this force, right? So all these things we have talked about through this center of mass, right? For the system of particles. Now we will understand about the rotational analog. So rotational analog we will understand. Okay. And so there would be a rotational analog of this linear displacement, linear velocity, momentum, acceleration, and then force. So there would be all these rotational analog, right, in rotational motion. And firstly, we will talk about the point particle, right? And then we will talk about this system of particles. So first we'll talk about the rotation of point particle, and then we'll talk about the system of particles. So this is the goal of this class, right? And before we start all these things, so let us recap what is the cross product, right? So what is the vector product, or what is the cross product? So we know that we have two vectors, right? Let's say this is A, and in normal representation, it has a magnitude and it has a direction, right? So if we write this vector A, so this length is magnitude, and this head of the arrow, right? This is A. Similarly, we have another vector which is whose magnitude is B, and its direction is B hat. Right, so we have another vector. So its magnitude is B, the length of the vector, and its head shows us the direction. So we know that if we multiply two vectors, and the result is also a vector, then that kind of multiplications, then that multiplication cross product or vector. Right? So it is given by two. So it is given in two ways. One obviously in the Cartesian way, and the other one is this normal vector. Right? So this is A, and this is cross of B. So this is given by A magnitude, B magnitude, sine theta, and then n hat. So part, this part is the magnitude part, right? So let's say we are, so we are multiplying a vector and we are getting another vector. That is called the vector product, right? So this C will have some magnitude and this C will have some direction. So that is represented by,
Sir,
yes,
isn't it should be like A into B is AB cos sine theta
yeah. So that is,
cross
yeah,
product, right?
yes.
Okay. Yes, sir.
Yeah, so that is what we have written, right? So I'm just saying that this product will also be a vector, right? And it will
Yes, sir.
contain the magnitude. So the magnitude part is given by this, and it will have a direction which is given by this, right? So let's
Yes,
say we have this vector which is A, and we have this vector which is, and if we are taking A cross B, right? So are we going in the clockwise or anti-clockwise? What is this? Clockwise or
anti-clockwise.
anti-clockwise, right? So we are going anti-clockwise. So this is A cross B, and this is,
Minus
yeah. So A B sine theta, and this n hat would be represented by this direction, right? Which is which is coming. This is given by. So let me. I have shown you this many a times, but Izan and all the other people are here. So we have these two vectors. This is A and this is B. So the direction of A cross B is given by the Maxwell's right hand thumb, right? So this this is our palm and this is the thumb, right? So if we place, this is the direction of the A vector, right? So if we place our fingertips in the direction of the A vector, and then we curl our palm, right? And then we curl our palm in the direction of B vector. So whatever is the direction is given by this thumb, so that would be the direction of A cross B, right? So let's say this is
yes,
one
sir.
plane. This is one plane, right? This is the plane of A and B. They are in the same plane, right? So then if I take the cross product of this A cross B, so that would be where? Going inside that plane or coming out of that plane? What would be that?
Out.
Outward, right? So the outward representation, it is denoted by this one. So let me, this outward representation is denoted by this dot. Okay. And the inward, so this is outward direction. And the inward direction is represented by this cross. This is inward direction. Okay. So that is how you get the direction of this n hat. So in this case, this would be n hat would be this outward direction, right? And if we are going clockwise, then what would be the direction? Yeah.
Sorry, sir.
If we are going clockwise, we are calculating B cross A. So what would be the direction? Yes,
Same.
same direction. B cross A,
Inward.
inward, right? B cross A. So we are going from, let's say, that. Yeah, so this is B. So our fingertips in the B direction, and we curl our finger in this direction. So this is inwards, right? So in the monitor, it is looking like outward, but it is, yeah. So then, if I calculate B cross A, so that would be AB sine theta, right? Magnitude would be same, but direction is negative of n hat, right? So I can say that. So I can say that A cross B, this is not equal to B cross A. Okay, and A cross B is equal to minus of B cross A. So we can clearly say that this is not commutative, right? Cross product is not commutative. Okay, this was about the cross product, and this is in the vector. Okay, so it has a Cartesian form also, right? So let's say that if we take three vectors, unit vectors. This is in x direction. What is this? Is on. What is the unit vector in x direction? Yeah, that we have done. So what is the unit vector in x direction? Is on. What is that? Okay, Akib, you tell me. What is the unit vector in x direction?
I cap.
I cap, right? So this is I cap in y direction. This is j
J
cap,
cap.
and it in the z direction it is k cap, right? These are the unit vectors in the x, y, z Cartesian axis, right? Cartesian coordinates. So let's say if I want to calculate I cross I, right? How much that it would. So I cross I would be I, magnitude of I, and then again magnitude of I, and then the angle between I and I. So sine theta. And what is the angle between I and I?
0.
0. So this is sine 0, right? So which means that magnitude of I is 1, this is 1, and sine 0 is 0. So all these will cancel. So similarly, if we calculate J cross J and K cross K, so all these would be 0. So these parts we have done already, but I'm just repeating things, right? Okay, so this we have understood. And what about I cross J, right? So I cross J would be how much?
K.
Yeah, so you already answered. Yeah. So I cross J would be magnitude of I, magnitude of J, sine of angle between I and J is 90. Right, so this is 1. And direction would be how much? So if we place our fingertips in I direction, curl it in J direction, so the thumbs will point out to the outward directions. That is J. Okay. So there is this cyclic rule that we follow. And in that, we can clearly see that what would be I cross J and J cross K and all. So whenever we are going in the clockwise or anti-clockwise, this is what? I to J
Clockwise.
clockwise. So whenever we are going clockwise, so that will give us positive. And whenever we are going anti-clockwise, right? So that will give us, like, these are the things we have to do. So simple example that we can understand is, let's say we have a vector, right? So let's say we have a vector whose magnitude is, so a vector of magnitude, let's say 4, is making an angle of angle of, let's say, 45 degree with another vector of magnitude 5, right? So find the vector product of first vector with the second, right? So we have first vector which is whose magnitude is 4. We have second vector whose magnitude is 5, and the angle between them is 45, right? So then we can find out the only we can find out the magnitude, right? So forget about the direction. So find the magnitude of vector product of first vector with the second. So magnitude is given by simply A, B, and sine theta. So A, which is 4, B is 5, and sine of 45. This is how much, guys? How much is sine 45?
1/√2.
1, right? So this is 1 by root 2. So we multiply by root 2, root 2. So this is 20 root 2 by 2. So this is 10. This is the magnitude, right? And one another question can be asked, what in the Cartesian form, right? So find the cross product of vectors A and B, where A is 3i plus 4j and B is 3j plus 4k, right? So this we have to find out. What would be the cross product of the. So then what we will use? So we will use these results, right? This one and this cyclic property, right? So one is also this matrix notation, but some of you guys don't have uh, my determinant and matrices. So you guys don't have mathematics. So we will use this Cartesian form, right? So A cross B, this would be 3I plus 4J cross, and this is 3J plus 4. So first we multiply 3I with 3J plus 4K, and then we multiply 4J with 3J plus right. So this would be how much? 3I cross 3J, and this is 3I cross 4K. This is 4J cross 3J, and this is 4J cross 4K. So we remember that I, J, and K. Right? If you are going in the clockwise, so this is positive. If you are going anti-clockwise, so that is. So this is 9, and I cross J is how much?
K.
K
K, right? So this is K, and 3 fours are 12, and I cross K. I cross
minus
K
J.
minus 2, right? And then J cross J,
0.
right? And then J cross K. So 16, and
I
J minus, right? So then this uh, new resultant or the cross product would be how much? 16I minus 12J plus 90. 90. So this is the cross. Right, so this was all about the cross product that we need in this chapter, right? So you guys please move down all these portions, and then we will understand about the rotational motion in system of one. And if you guys have any question, please ask. Oh, and there is also this question that I will ask. Yeah, so the question from the vector. Yeah, whenever you guys want me to scroll down, please tell. Yes, whenever you guys want me to scroll down, please tell.
Finish, sir.
Yes, guys. Whenever you guys have noted it down, please check.
Done, sir.
Yes, done, guys.
Yes, sir.
Yes, sir.
Yes, done, guys.
Yes, sir.
Done, sir.
Then please stop this last part and then we'll go back to the rotational. Whenever you guys have noted it down, please
Done, sir.
done. Okay, everyone noted. So
Yes, sir.
Yes, sir.
then let us start. So there is one question. So please take this question as well. Uh, this is from the Instagram. Right? So you have a vector A, which is 3i minus 4j plus 5k, and you have another vector which is minus 2i plus j plus 3k. So then you have to find out the cross product of these two, right? So please solve this and tell me the answer in the next. Okay, please note it down. Right,
Yes, sir.
noted. Yeah, noted everyone.
Yes, sir.
Yes, sir.
Okay, so the next thing is the rotational motion. Right, and for now we are talking about a point part.
Sir, we have to do that question.
Yeah, yeah. So not now, but at your home, right?
Okay.
Not. We want to reach up to, yeah, principle of movements and at least center of gravity. That part I will teach. Okay, so rotational motion of a particle, right? So let's say we have this axis of rotation, and through axis of rotation, this thing is so this point particle mass m is moving in this circle, right? So let's say it will create or it will create some distance, right? Or it will achieve some distance from this point to this point, right? And that displacement is called the angular displacement, right? So the angle subtended between the initial point to the final point through this center, right? So this is the point of observation in which we are measuring the angle. So from point of observation, the angle subtended between, let's say, A and B, right? So that is called the angular displacement. And this we have done already. So that is represented by this theta, right? And then we have this angular velocity. Okay, so all these things we have done in the which chapter we have done this part? So in the third chapter, motion in a plane, right? So when we
Yes,
were
sir.
yeah, when we were talking about motion in a plane, so all these things we have done. So angular velocity is this axis of rotation. So this axis of rotation is rotating with some velocity, and that velocity is called the angular velocity. And instantaneous angular velocity, this is represented by d theta by dt, right? So this is omega, which is d theta by dt. So if we are moving in the clockwise direction, or let's say if we are moving in the anti-clockwise direction. So for anti-clockwise, right, let's say this is the axis of rotation, this is we are moving in this way. So what would be the direction of the angular velocity, right? Or what would be, it would be positive or negative. So we are moving, this is what? Anti-clockwise, right? So for anti-clockwise, this would be what? Positive or negative?
Negative?
Yeah, because again we apply the screw rule, right? Maxwell right hand thumb rule. So if we curl our finger in this direction, right? So then the direction which is going in the upward direction, so that will be positive, right? Is that clear? Because it is pointing out upwards. Upwards is positive, right?
Yes, sir.
Or let's say you are talking about this plane. So in this plane, you are moving in this direction. So if you are moving in that direction, so your thumb will point out outwards, coming out of this screen, right? So then this is your axis of rotation. So then this is coming out of the screen, so that is positive. And if you are going clockwise, then this is negative. So always just remember this Maxwell's thumb, right? Then you will get the answer. Okay, so this was about the angular velocity, and this angular velocity is related with this linear velocity. So this is the tangent. The tangent shows you this linear velocity, and this is the displacement r, right? So this linear velocity is a relation between angular velocity and linear velocity. So your linear velocity is omega cross r. This we have understood, right? So if we are talking about the 90-degree angle, so this would be V would be omega, right? If omega and R are making the 90-degree angle, so at this point, right? This is the R. So this would be velocity, and this is so this R and omega are 90 degree. So then this would be omega R, right? So this relation we have already talked about, right? You guys
Yes,
remember?
sir.
Yeah, and this we have done to prove the centripetal acceleration. So when we're talking about the centripetal acceleration, we use this quantity. So this is about the relation between angular velocity and linear velocity, right? And these are the portions that we have done already, so that's why I'm just rushing through it, right? Okay, and then you have this angular acceleration. And to be precise, this is instantaneous, right? So instantaneous angular acceleration alpha, and this would be again the rotational analog. What is acceleration? Acceleration is dv by dt, right?
Yes, sir.
So if we take the rotational analog, so what would be that? This is linear velocity, right?
Dx by dt.
No, no, no. So we are talking about acceleration. What is the rotational analog of velocity? What is the rotational analog of linear velocity? That would be angular velocity, right? Right?
Yes.
So this would be d omega by dt, right? Correct. So this vector is d omega by dt. And if we are taking the constant angular velocity, so this would be simply, right? The direction is similar. So then this would be d omega by dt. Okay. Because when the direction is same, then this vector part would be not there. So this would be simply d omega by dt. Okay. This is
Yes, sir.
this is the angular acceleration, right? And now coming to the crucial point or the important point, that what is the angular, what is angular? This is represented by moment of, right, and the rotational analog of, rotational analog of the linear. And how much is this? So this angular momentum L, this is defined as R cross, right, where this R is the distance position vector, right, from the axis of rotation, and this P is the momentum. So whenever we talk about moment of something, right, then this R cross would be there. So if I talk about moment of force, then what would be that? If I talk about moment of force, so what would be that? Can you guys guess? Can you guys guess that? What would be that?
So forces, um,
F, right? Force is F.
F,
And
uh,
moment of
D.
force. So whenever we talk about moment of something, so we write R cross. So moment of force would be R cross. Is that clear?
Yes, sir.
Okay, so we'll talk about that later. So this is how we define the angle, right? And the dimension of angular momentum would be how much? So this is meter, and this is kg meter. So kg meter square. Kg, this is R is meter, right? This is mass into velocity. So this is kg meter per second. So this angular momentum L would be how much? Kg meter square per second. This is the angle. Okay, and this is related with this force. So let's see that how it is related. Yes, this is, and the dimension of this. So this is a vector quantity, right? And SI unit is kg meter square per second square, and the dimension dimension would be simply what? This is ml square t minus. This is the dimension. Okay. Now the next part is rotational analog of force. That we call torque, right? So torque is what? So this is moment of force, and this is defined as R cross F. So let's say you have this axis of rotation, and this is the point of observation. And let's say you have this point, and some force is acting in this direction. This is x, this is y, and let's say this is z axis. Okay, and the force is acting in this direction, and this is the position vector r, and it is making an angle theta with this vector, right? So this R cross F would be right. So this R cross F, and what would be the direction of the R cross F? This is R, right? So R cross
So
F would
I cap, J cap,
no. Yeah, so that
I
would be
comma J.
I comma J. So R is not in the X direction. X is this, right? So this torque would be in this direction, okay, perpendicular to this direction. Is this part clear? So the let me show you guys. So R is going like this, right? And you have this F. So R, your fingertips in the R direction, and then cross F. So then you move your fingers in the force direction, right? So this is R cross F. So it is coming out of the screen, right? Of this plane. So this would be in this direction. So this is the direction of the torque. Is this part clear?
Yes, sir.
And then what is the, so this force has a line of force. So this is the line of force. Okay. And from R, what is the distance which is perpendicular to this R? This is the line of force. So this is the perpendicular distance, right? Is this part clear?
Yes, sir.
So this is perpendicular distance, and this magnitude of torque would be RF sine theta, because R perpendicular is R sine. Okay, this is your R, right? So this would be R, this is your R, right? And it is making an angle theta. So this would be your R cos theta, and this is your R sine theta, which is equal to this. This is R sine theta, and this is your R cos. So this is the magnitude of storm. Okay. So this is this part clear, everyone?
Yes, sir.
This is all about the rotational analog of velocity, acceleration, and then this torque. And then we will write this in the form of system of particles, right? So first we will write this in this way, and then we will write the whole system of particles. So you guys please note down this, and then we will write about the relation between this torque and then angle. So please note down up to this.
Yes, sir.
Yeah, whenever you guys want me to scroll down, please tell me.
Finish, sir.
So these parts we have already done, so that is why I did not talk about these. Right? So extensively we didn't talk about, because these we have already done, right? All of you guys. got disconnected. So yeah, Izan got disconnected. Yes, whenever you guys have noted down, please tell me.
Finished, sir.
Well, why did I write? This is velocity. Velocity is v first. Right. Whenever you guys have noted it down, please tell me.
Finished, sir.
This is r, right? This is theta. This is r cos theta, and vertical part is r sin theta, right? So this is the distance, perpendicular distance with this force, right? So this is the line of force and the perpendicular distance between the force and this position vector. So that is r line, r sin theta, right? Or r perpendicular.
Finished, sir.
Okay, so all of you guys have noted it down. Yes, everyone.
Yes, sir.
Good. So can you guys tell me about the Newton second law? What was the Newton's second law?
M into A.
So that was something like rate of something, which is so Newton's
Sir,
second law gives, yeah, gives the
rate
force.
of change of momentum directly proportional to applied force.
Yes. So this is the Newton's second law, right?
Yes, sir.
So we are talking about the rotational analogs, right? So there would be some rotational analog of this one also, right? So let us find out, and that is given by the relation between, so relation between the angular momentum and the torque. Right? So what is the relation between the angular momentum and torque? So we know that L is R cross B. Right? This moment of momentum. Right? So angular momentum is what? Moment of momentum. And I have already told you guys that whenever we are calculating moment of, then there would be R cross. Right? So moment of momentum is angular. Now let us differentiate with respect to t, with respect to time in both these sides. So this is dl by dt, and this is d by dt of r cross. And so we are going to use this product, right? So first we will put r as a constant and take the differentiation of dp by dt. And then we will take the, so this is a cross product, so the direction or the right hand and left hand is very important, right? So you have to take the differentiation of first, and then this is cross, right? This is this part here?
Yes, sir.
So what is momentum, everyone? What is momentum? That is mass into velocity. And what is dr by dt? What is rate of change of displacement? This is
0.
rate of change of displacement. This we have done so many times in calculation. This is the thing that we talked about. Okay, what is dx by dt? Yes, rate of change of distance displacement.
Sir, instantaneous velocity.
So instantaneous velocity. This is instantaneous velocity, right?
Sir, how come dr by dt?
This is your position, right? And if you take the differentiation with respect to position, then this is velocity, right?
Okay, sir.
Yeah. So keeping these and dp by dt, you guys just now, right? So this is how much. This you just have
Sir,
to
what is p?
momentum, momentum. The moment of momentum we are calculating, right? Did I not write this part? Let me write that this is linear momentum. Right. So this is the momentum. R is the position. Okay. Yeah. So rate of change of momentum force you have just told me, Akif. Right.
Yes, sir.
Okay. So putting all these values in here. This is R cross F, and this is V cross M V. Right. So this is dl by dt. R cross F is how much? Moment of force. Moment of force
Torque.
is torque, right? This is torque plus M I can take outside. That is a constant. What would be the cross product of same quantity? P cross V, what would be that? I cross I is what?
0.
P cross V would be how much? P cross V would
0.
be Yeah, E cross V would be V into V into sine of right? So this is E cross this is then we got this relation. So this is the rotational analog of Newton's second law, right? So torque is the change of rate of change of angle. So this is this point here, everyone?
Yes, sir.
Please move down from this part. You guys have noted, right? So now let us. Yeah, whenever you guys have noted down, please that I can scroll down.
Can you scroll?
Yeah, whenever you guys have noted it down.
Finished, sir.
Done.
Okay, so then if I have like so if I have a torque which is zero, so if T is zero, then what will happen? Then dl by dt is zero, right? So
Yes.
if dl by dt is zero, so what is the differentiation? So when the differentiation of something is zero, right? When the differentiation is zero for something,
When there is a constant.
constant, right? So which means that L is a constant, right? So if the external torque, if the external torque is zero, then angular momentum be right. So this is all about the angle. So we were talking about the point part, right? So we were talking about the point particle. Now let us write everything in the form of the system of particles. So rotational motion, rotational motion system of particles. Right. So we have a rigid body, right? And this is the axis of rotation. It is moving with constant angular velocity, and all these m1, m2, all these things are there, right? So then what would be the angular momentum? So total angular momentum, this would be, let's say for one particle, this would be Ri cross Pi, right? So this is Li. Right, for each particle, this is Li here. And total would be summation of L, right? So I'm writing in this way. Let's say that L1 is R1 cross P1. Similarly, L2 is R2 cross P2. Right. Similarly, L3 is R3 cross P2. So I can write the total L as L1 plus L2 plus L3 plus L, let's say n number of particles, right? So there is a shorthand notation that I can write this as summation of all those individual angular momentums, right? Where it is I goes from 1 to n. This is a shorthand notation, right? And we already know that from the Newton's second law of rotation analysis, right? So tau would be, this would be dl by dt. This would be how much? This would be d by dt of the summation of I equal to 1n, and right, this is the total tau, which is tau 1 plus tau 2 plus tau 3 plus plus tau 2. And so total external torque, this is total external torque. This would be d by dt of all these individual angle momentums. Okay. And if tau external is 0, right? So which will show us that this L total angular momentum is constant, right? So this is the constant. This would be a constant. This is the conservation of angular. Okay. So all these things we have done it all, right? So we did for the case of, yeah, guys. So we did this for the case of the linear translation motion. In translation motion, we got the similar result, right? For F external, if F external is 0, then linear momentum is conserved. Similarly, when the external torque is 0, so whenever this external torque is 0 for system of particles, then this angular momentum would be conserved. These are the things that I wanted to do, right? So please note down for any confusion, guys? Any question, any doubt?
No, sir.
And do you guys remember this fourth chapter, laws of motion?
Yes.
So, guys, remember that if all the external forces were zero, so then what did we say about that object? Yeah.
At rest.
That was at equilibrium, right?
Yes,
If
sir.
all the forces were zero acting on that object, then that object was at equilibrium, right? So that and then we talk about this. Whenever you guys want me to scroll down to that,
Can you scroll?
this is the total torque.
Can you scroll? Done, sir.
Then, Akib and what about
Done, sir.
next topic as we discussed in the laws of movement, right? The next topic is not because we don't have any object, point object, we have system of particles. Then we'll talk about the equilibrium of rigid body. The rigid body will have two kinds of one would be translation equilibrium, and the other one would be rotational. So when we will say that the body is at translation equilibrium, so when all the external forces, right, acting on it is zero. So when all the forces F1, F2, F3 acting on that object, so when that is zero, so that would be called translation. And for the case of rotational case, So all the external torque would be zero, right? So tau 1 plus tau 2 plus tau 3 plus tau n, this is zero. So this is called the rotational. But you can have also some examples when the rigid body is in partial equilibrium, right? So in partial equilibrium, either the body is in translational equilibrium or in the rotational. So, for example, let us take a massless rod. Right, so we have this massless rod. Let's take a two example. And one force is acting in this direction, right? And the other force, which is of the same amount, this is acting in this direction. Okay. And the rotation of this object is, so this is rotating in this way, this is rotating. Okay. So this object, so does this object has a translation equilibrium? Is this F1 and F2 cancellable?
No.
So F1 plus F2 is not equal to 0. So this is not in translation, right?
Sir.
But this object is moving, so this part is moving in the clockwise or anti-clockwise. This is moving in anti-clockwise,
Anti-clockwise.
right? This is moving in,
Clockwise.
so this has a rotational equilibrium, right? So tau 1 plus tau 2 is this has a rotational, right? And let's take this example. So we have this bar and this is moving in this way and this is moving in this way, right? So then, and this is rotating in this way and this is rotating in that way, right? So F1 and F2, is this what kind of equilibrium do we have? Do we have translation equilibrium? Yes. F1 plus F2.
No.
This is no, because this is going in this direction and it is pulling in upward direction. So we have two forces. One is moving upward, one is pulling upward, and another one is pulling down. So both are balancing, right? So we
Okay,
have
sir.
a translation equilibrium. But what about, so this is anti-clockwise, right? And this is again anti, right? So do we have rotational equilibrium? Not. So this is not rotational. So all these are example of partial equilibrium. Okay. You can have the translation equilibrium, but not the rotational. Also, you can have the rotational equilibrium, but not the translation. So please note it down, and if you guys have any question, please ask. Yeah. So then we'll stop at here. Next class will do this principle of That part is very important. Yeah, whenever you guys want me to scroll down, please.
Finish, sir.
Please note down these two examples. They're very